You ever look at a chart from a science class and it just looks like some kind of crazy map? Well, that's pretty much what we're diving into today. This isn't just any map, though. It's a map of a cosmic journey, where every single thing on it is on a quest for just one thing: stability.
Okay, so what you're looking at here is what's called a radioactive decay chain. You can kind of think of it like a set of dominoes, right? Each unstable atom or isotope, it topples over, and that triggers the next one, and they keep changing as they go. But look closely. See how all these different paths, they all end up in the exact same spot? The real question is, why there? Right, so this is the heart of the mystery. We got to figure out our final destination. I mean, with all these complex atomic journeys happening, all these transformations, why do they all funnel down and stop right here at cobalt 59? What's so special about this one? And you know what? The answer is actually super simple. It's because it's stable. That's it. While every other element on this map is jumping around, constantly changing, cobalt 59, it's just chill. It's at peace. Its nucleus has that perfect recipe of protons and neutrons, so it holds together. It's not going anywhere. It's done. It's reached the finish line. It found its stability.
But okay, how do all these other elements get there? If you squint at our map, you'll see a few little question marks, right? Some missing pieces of the puzzle. So, this is where we get to put on our detective hats. We're going to fill in the blanks on this atomic map. So our first case to crack is this jump right here, from scandium 59 over to titanium 59. Now what's weird is they both have the same mass number, 59, but they're totally different elements. So what in the world is going on inside that atom to make that happen? What kind of decay does that?
Well, the answer is this really cool thing called beta minus decay. It's almost like a tiny magic trick happening deep inside the atom's core. You've got a neutron, which has no charge, and poof, it turns into a proton, which is positive. Now, to keep everything balanced, it has to spit out an electron. That's the beta particle. And boom, just like that, you've got one extra proton, which means you have a brand new element. And this little equation shows it perfectly. Scandium starts out with 21 protons. It goes through that beta minus decay, and it turns into titanium, which, yep, has 22 protons. The mass number, 59, doesn't change at all. So, mission accomplished. Path number 1, decoded.
Okay, next puzzle up. Little further down the chain, we see copper 59 changing into nickel 59. And again, same deal. Mass number is the same, but it's a different element. So what's the trick this time around?
For this one, we need a totally different tool. It's called beta plus decay. It's basically the exact opposite of what we just saw. This time, a proton turns into a neutron. And to make the math work, it spits out something called a positron. It's like an electron's twin, but with a positive charge. Pretty wild, right?
So what happens is, copper, which has 29 protons, suddenly becomes nickel with 28. The atomic number just dropped by 1. And just like that, another piece of our cosmic map clicks right into place. We're getting so close now. Okay, this is where things get really interesting. Let's play a little what-if game. What about a slightly different version, an isotope of our hero element? Let's take a quick side trip and check out the story of its unstable cousin, cobalt 60. So while our cobalt 59 is the stable, chilled-out hero of the story, cobalt 60 is kind of its wild, radioactive cousin. I mean, they're nearly identical. The only difference is one single neutron. So how can one be the final destination while the other is just another stop on a completely different journey? What's the deal?
It really just boils down to a simple rule of thumb in the atomic world. Pairs are better. Think of it like this. Nuclei just seem to be happier, more stable, when they have even numbers of protons and neutrons. It's just cozier. Cobalt 60, with its odd numbers, is kind of fidgety and restless, so it's always going to want to decay into something more stable, like nickel 60, which has those nice, comfy, even numbers. And because it's so unstable, cobalt 60 decays at a super predictable rate. We measure this with something called a half-life. That's just the time it takes for half the stuff to disappear. So let's do a quick calculation. If its half-life is 5.27 years, what percentage of it would be left after just 3 years? Well, the logic is pretty simple, right? We know if we wait the full 5.27 years, exactly half of it, 50%, would be gone. But we're only waiting 3 years, so we're stopping the clock a bit early. That means we should definitely have more than half of it left over. And yep, when you actually do the math, that's exactly what you find.
After 3 years have passed, 67.4% of that original cobalt-60 is still there, just hanging out, waiting for its turn to transform. Okay, so we've mapped out the journey, we've figured out how it all works, we've even taken a little side trip. But what's the point of all this? What's the ultimate payoff for all this decaying and transforming? The answer, my friends, is energy, and I mean a lot of it.
Let's take a step back and look at the whole shebang. We start with our stable buddy cobalt-59. We add a neutron, which turns it into the unstable cobalt-60. Then we just let it do its thing and decay into stable nickel-60. The whole secret, the key to everything, is hidden right here in these teeny tiny, almost unnoticeable differences in mass. Because when you add up all the mass before the reaction and then you add it all up after, something absolutely incredible happens. A tiny little bit of mass has just vanished. But thanks to our old friend Einstein and his famous equation, E equals mc squared, we know it didn't just disappear. It was converted into a mind-boggling amount of energy. We're talking 944 mega-electron volts. On an atomic scale, that is a ton of power. And you want to know what's really cool? That little negative sign? In the world of physics, a negative sign here is awesome news. It means you don't have to put energy in to make this happen. It actually pays you energy out. It's releasing a huge amount of energy out into the universe.
So let's bring it all home. We started out with what looked like a pretty standard question from a chemistry test, right? But by decoding that one little map, we've actually uncovered one of the most fundamental rules of the entire universe. That locked away inside the tiny, tiny nucleus of an atom is an amount of power that is almost impossible to imagine. This whole quest for stability, it isn't just some random journey. It's one of the engines that makes the whole cosmos run.